Hey, sorry about that. I only just spotted your email.
No problem, no problem, no problem. I'm actually very close to the end of these, so then I want to talk about Spacetime and Chapman and Cog. There is a lot of lumpiness here in the space.
Yeah. Islands of manifolds.
Yeah. I think I've seen most of these already. It's encouraging. I think we're pretty much there. I'm as a long time hunter trapper of computational animals, I can say we've seen most of them. Ooh, that's a lovely one. Look at that lovely one. And that one's nice too. Look at that, how simple that one is.
It's pretty nice.
I mean, who knows how it works?
That looks quite hyperbolic, the middle one.
Yeah, there are more hyperbolic. These are not optimized for hyperbolicity. There's ones that
I look forward to the classification theorem for finite simple manifolds. It's just such a ridiculous concept. I think it'd be quite funny.
Well, why not? I mean, why shouldn't there be such a theorem? I mean, there must be. See, what's interesting is that some fraction of these have nice integer dimension and some fraction are very unruly.
Mm-hmm.
That's one we haven't seen. It's a new manifold on the block, so to speak. See, some of these will be nice models of some space-timey type things.
Yeah, I mean the sort of trumpet thing you sent earlier looked a lot. I mean, it looks a lot like a representation of a black hole in ADM or something.
Indeed, that had not escaped my notice.
Right.
I mean, and I haven't even tried to compute the causal graphs for these things.
That's going to be fun.
Let's do one just for fun. Let's just take this guy. Well, it looks very much like the manifold itself.
Which is what we'd want, yeah.
Well, look at that thing. There it is, light cones and all. I mean, it's a two-dimensional surface.
Looks like a Penrose diagram.
You're not supposed to be able to generate those like this. I have to say, I am getting so optimistic about this whole thing. I really, well, look at that weird creature with the threefold. I also think we should probably have some gallery of these 3D things because we can have them animatable on the web. I mean,
yeah, that's going to be fun.
Just a lot of work to do, you know. Okay, well, that's cool that thing has a very nice, simple causal graph.
Yeah.
So we've got probably some really nice models here of various kinds of space times and so on. All right. You know what? My addiction is, I'm almost through my addiction because I'm almost at the end of the ones I've generated. And I'm failing to find anything new anymore. I mean, I've pretty much seen everything that's here. I don't think that one's interesting. That one's just a, yep, nothing new in that one. I think this feature space plot way of doing this is quite useful. I mean, it's quite, because I don't even have to look over here. I don't think I'm going to find anything new anymore. We've seen all of that. We've seen that guy. That guy is very, somehow, that one is really cool in 3D, as I said.
Yeah.
Well, somebody can have fun at some point in the next few years discovering what I failed to notice. the number of such things from the NKS book is unbelievably small. Because I did many things like this, obviously, for that. And I'm still waiting for people to find, oh, you missed some register machine that's interesting, or
right.
What happened there? For some reason, counter 342 didn't generate a picture, and I don't know why. It may have timed out. See, that one is very fertile. I think we've seen that guy before. Oh, that one's fun. So some of these are very, anyway, I think it'll be interesting to try and identify what the actual manifolds are, and we can just measure some, because I can get these embedding things, I should be able to measure. I see, that's kind of fun. It's going to end up being, that guy is kind of interesting, actually.
Yeah, what the hell is that?
Who knows? I haven't seen one of those quite like that before.
It's a one-dimensional manifold.
Yes, it probably is. We have many one-dimensional manifolds, but not ones that are knotted or anything.
No, this is, one-dimensional, but with a non-trivial topology. This is so cool.
I think, kind of everything will be here at some point. Yeah, I agree with you that there needs to be a classification theorem.
Right. Do we have a notion of tensor products of rules?
No, we easily could have. You just put two rules together and see what happens. The updating order will matter.
Yeah, I might try and formalize that, because it may, instinctively I feel like, large swathes of these things should be factorizable in some sense.
Yes, that's a good point. Well, okay, so that's a good question, is could a rule be factorable?
Right.
We've seen those pine cones a lot. We're done. It's pink. We're over. It's over. Pink means we're done.
That's where it failed.
Yeah, that's where it failed. Okay, let's talk about space-time. And then I have to figure out how I'm going to organize talking about this stuff. I think I'm going to show some stuff in the section on zoology, and then I'm going to come back to it in the section on manifolds and talk about the identification of these things with manifolds. And actually talk about, this one is such and such a manifold and the limit and so on.
Okay, that sounds good.
All right, let's talk about space-time. And this is our inspiration picture for our discussion of space-time.
I really like that.
Yeah, okay. So your claim is that we look at n sub r of, are we calling it t and x like that?
You said that there were syntactical reasons for preferring it that way, so we can do that.
I think so. I don't know why, the cellular automaton function has t first and then x.
Right.
And I think it generally,
I guess it's because you're doing like an operator form almost.
Oh yeah, that's right.
So maybe that is the right way to think about it.
Okay, so this is the function, and that function has, it's a function at every point in space.
Right.
Every point on the causal graph, and or on the space graph.
Right.
Although probably more interestingly on the causal graph.
Yes, and it has slightly different structure depending on whether it's the space graph or the causal graph. Because on the causal graph, you effectively have to define, R is not just a scalar, it's a, In the way I formulated it,
Cone.
it's a time vector.
Okay. But is it just one time vector, or is it all possible? Is it the whole cone of time vectors?
It's just a single time vector, because if you know what the time vector is, the time vector defines locally what the cone is. It's the time vector tells you what the foliation is at that point. The sort of the local foliation of the causal graph.
I see.
And then
Which
you can
defines a cone, which is the generator of a cone, basically.
Right, precisely. It's exactly. Yeah, exactly. So you take the set of geodesics that emanate from a single point subject to that time vector, and that gives you the space-time cone.
Wait a minute. Given a point on the causal graph, there is a cone. Period. End of story.
But you don't know how the causal graph has been foliated.
Okay, let's take this guy as an example. Okay, and let's say we are at a particular point here.
Mm-hmm.
It's a bit annoying that it's in 3D. Okay, so here we've got a point, and it goes up to that one and down to this one.
Right.
And across to this one.
Right.
So what are you saying? So you're saying that some of those vectors are not time-like.
Right. So there's a default, unlike the conventional way you think about special relativity, there is actually a default foliation. There is a default decomposition into initial reference frames, because you can just do a kind of, layered graph embedding or something. And that gives you the default foliation in which the downwards arrow, the downwards facing edges are all time-like.
No, but that depends on the updating order.
Right. Well, which is another way of saying that's a kind of tautological statement, right? That the foliation depends on the foliation, or the updating order depends on the updating order.
Right, but so this is a causal for a given updating order.
Yeah. So yeah, exactly. So I know I completely agree that if you prefix the updating order, then obviously every point has an associated light cone. It gives you the space-time
Right. For
cone.
a given updating order, there is a definite light cone.
Right.
For every point. Okay.
Yeah. So the point is that the time vector is a way of defining locally what the updating order is without having to decree a global updating order for the whole causal graph.
I don't understand that. You need the multi-way causal graph to do that, don't you?
No.
Why?
No. Because if you have a causally invariant system, which I'm assuming.
Okay. Assuming causal invariance, there is a unique causal graph.
Right.
And then updating orders are just slicings of the graph, are just layerings of the graph.
Right. So the time vector is really telling you the local normal vector for a hyperslice.
Right. And your claim is that there is a default that is to just look at, one edge is one depth, one increase in depth type thing.
Right.
Okay. It is good to have our inspirational light cone here.
Right. I mean, do you know about the notion of downward plane or upward planar embedding, or in this case, downward planar embedding?
No, I do not. What is that?
So if you formulate layered graph embedding as a sort of optimization problem, the downward or upward planar embedding is the ideal case of that. So in effect, you have no crossings of edges.
I see. Downward planar embedding is a non-crossing layered embedding.
Yes. So that's not guaranteed to exist for a general DAG, but it's the ideal case when it does exist.
Right, but it may not exist even for very elementary cases here. It may not exist. That's a useful concept. I agree. That's a useful concept.
Right. But in any case, there will be an optimal solution to the layered graph embedding problem, and that, in effect, you can think of as being a default foliation.
Right. Okay. All right. So,
which is a little bit concerning because it does imply that there exists a preferred reference frame. But
what the hell's the rest frame of the cosmic microwave background?
Well, yeah, I guess, yeah, fair enough. There's probably an interesting master species.
That ship already sailed.
Yeah. But I mean, someone should definitely go through and figure out the details of like how this relates to Mach's principle and all that.
Indeed.
But I haven't done that yet.
Right. I wouldn't worry too much about that. I mean, as I say, there is a preferred reference frame in our universe, so
Right. But if it turns out that the cosmic microwave background is somehow related to layered graph embeddings, it's going to be pretty funny.
Well, right. I mean, that it is the preferred reference frame of the universe, right? So therefore, this would be, right. Okay. But anyway, let's keep going here for a second. Okay. So now we've got this function, which you have got. You are able to expand that function. So n sub r of t. You have an expansion of that function. So in a first approximation, that function is like, r to the d times 1 plus r squared, well, r times r squared times whatever, right?
Yep.
Plus ... Okay. Okay. Now, if there is local variation in D, that shows up as a log R term, does it not?
Yes.
So if I write R to the D, I'm expanding in what happens if I just say series of that R about 0 to order 3. Okay. Right. So there's a linear term in R log R, which is kind of bizarre. Okay, so from variation of dimension, I don't quite understand the linearity there because I would have expected that the thing has no, the R squared is nice and direction independent.
Not for a causal graph.
Fair enough. Okay, but in this case, this is telling us that there's an R log R so for small r, okay, so the main point is there's that cusp.
Yep.
I wonder what the significance of that is. If you were a geodesic, it would probably have a big effect on you to have well, anyway, okay, all right, fine. Okay. So the next question is, so with different choices of foliations, NR of T and X is different.
Mhm.
Dandy. Okay, given a particular foliation, particular choice of gauge, effectively,
Mhm.
what can you say about the T and X dependence of N of R, N sub R?
Well, not a whole lot in general.
Okay,
Because the
yeah.
dynamics of this thing. Yeah, sorry, go on.
Okay, but let's look at let's start off with the continuity equation.
Mhm. Right.
Okay, so as we look at, let's look at T plus delta T.
Mhm.
Okay, is there a Gauss's law continuity idea? That is, take a bigger volume and you know there are a certain number of nodes in that volume, in that space-time volume.
Yes. There's a pigeonhole principle argument you can make along those lines.
But right, but so as we perturb T and X, there's got to be some, I mean, there's got to be some, probably some continuity to the values of N sub R as a function of T and X.
Yes. Yes.
And is that in fact your continuity equation for the, okay, so what is your definition of the energy momentum tensor, given this?
Yes, I need to, okay, I need to figure out if this approach is equivalent to my approach. It probably is, but there may be some subtlety that I'm missing. So my definition of the energy momentum tensor is you pick a hyperslice in the causal graph that gives you your x nu, and then you figure out what is, okay, so then you have, okay, you have non-planar pieces of the, of a spatial hypergraph that we assume are behaving like elementary particles. And they have certain irreducible crossings of edges. There are, you can count the number of hyperedges that are bound up in non-planar pieces of the network. And then you can compute the flux through that hyperslice, basically how many edges, bound up in non-planar pieces of the hypergraph are moving through that hyperslice.
Okay.
And
that, by moving, by just co-moving in time.
Yes, right.
They don't change. They just move.
Exactly. They just pass through.
Okay, they're non-interacting. Okay, so non-interacting lumps just propagate unchanged through, well, quotes time.
Yes.
For any given foliation. But the foliation itself, by virtue of its chartiness, so to speak, can have an effect on this.
Yes. Right.
And so what you need to compare is your lumps are kind of the ground truth, but as you try to go through n, this n function, if n changes, your lumps will do different things.
Yes.
Right? So what is the relationship between a lump?
So the way that I've been treating this is when you have a lump, it's essentially because of Kuratowski's theorem and generalizations of it, that lump constitutes a portion of the hypergraph that is more densely connected than the background hypergraph.
Okay.
Okay. So then what happens is if you then try and do this dimensionality calculation, if you try and evaluate n.
But by the way, the thing that bothers me about that, so I made some simulations of that, okay? And if you are a geodesic, you prefer to go, oh, let's see, no, actually, there are two effects, right? I mean, so in an embedding, it depends what the embedding looks like.
Right.
The embedding can bubble up where there's more of that stuff. And so, yeah, I mean, we need to do that explicitly. We need to just put the Schwarzschild metric on a mesh and see what happens. Get what I'm saying? I mean, I did the beginnings of the, can you do that? Because there's all that stuff with the mesh connectivity graph and so on.
Yep. Okay. I'll investigate.
I mean, we might want to do that together because I already did a bunch of that stuff, and it was a little messy, but I think it needs an understanding of the coordinates for Schwarzschild metrics and so on, which
Yes.
I only partially have. Let's put that on the list of things to do, because I think that's a thing that's highly interesting, because you can actually look at particles propagating. I mean, you can actually look at geodesics on the mesh.
Yep.
Okay.
I think we should do that.
Okay, fine. Well, I can show you what I've got there, and you could maybe finish it. I mean, okay. So, all right. So, what you're saying, I mean, that intuition tells you geodesics clump together in places where, there's some change of behavior when you change the network structure. The geodesics do certain things, and you are describing here your quotes continuity equation is in effect a continuity equation for geodesics, if I'm not mistaken.
Yes. Right.
Okay. AKA, it's a so given a path, a geodesic, it approaches some part of the graph. Oh boy, there's got to be a way of thinking about this in terms of paths. What is the? So you have a bundle of geodesics. I mean, you could have more geodesics in a region where, no, you couldn't. That's okay. How to think about this? Every particle is on a geodesic, so there's a cloud of particles, and we ask the question, how does that? Yeah, right. How does the cloud? How does a cloud of geodesics, a bundle of geodesics, get thicker and not? And that is presumably the geodesic deviation equation.
Yes, right. It's computable directly from the discrete Ricci tensor.
Okay, let me look at this. So geodesic deviation equation, which would give us for a given, is this what sectional curvature is? I don't even know what it is, but for a given slice of the geodesic bundle characterized by proper time, right? Because it's parameterized by proper time.
Yep.
Okay, for that given slice, we can ask the question, we can ask what the volume effectively of the bundle is, what the cross-sectional area of the bundle is at that point. What the cross-sectional shape of the bundle is.
Right.
Okay, how is that related to sectional curvature?
So the sectional curvature, yeah, in effect, the sectional curvature is the Gauss curvature of that cross section.
Okay.
I think there's a way to think about that.
So let's think about that for a second. So okay, so by the way, we should be able to make some nice pictures of this, of what this bundle looks like as it propagates through these various spacetimes.
Right.
By the way, let me suggest as a practical setup for, let's make sure that your paper stays, goes through the theory, and you don't start trying to do all kinds of simulations, because I think the thing will be never ending if you try and do that.
No, I agree. It's already getting longer than I would like.
Right. I think you should, stick with the NKS pictures as, I don't think you probably need much else. and then it's the theoretical derivation, including, and it's not totally obvious to me that you should put the automated theorem proving stuff in there. It's not totally obvious to me. You shouldn't have a separate thing whose main point is the relationship between automated theorem proving and general relativity.
I mean, to an extent, I need it to derive Lorentz transformations. That's
Okay,
the
fine.
only place where it currently exists.
Then put it in there. Put it in it. But then I would break off that actual derivation as an appendix so people can, so it's a somewhat standalone, cognitively standalone object.
Yeah, that's a good idea, because otherwise this is going to be totally incomprehensible. As in, I think the only possible readership would be basically me.
Right. Right. So
there was a wonderful line in somewhere here. Let me see if I can find it. Yeah, I have a sentence here that mentions relativistic mass, the Seymour-Robertson theorem, De Broglie indices, and lambda abstractions in one sentence.
That's good. That's good. that's a classic. It's almost worthy of Roger Penrose and his or René Thom, who used to talk about blue sky, algebraic topology, and some biological thing. Okay. In any case, all right. So I'd like to understand this point about sectional curvature, but basically you're saying that, okay, so this is basically this continuity equation is essentially a restatement of the structure of the background space-time. It has no fine.
And you can consider it to be a continuity equation for geodesics, but because in the causal graph, the geodesics define the cones and the cones define n sub r, it's also possible to think of it as a continuity equation for vertices.
Okay, so Jonathan claims this is also a continuity equation for vertices. That is not obvious to me. I don't understand that. Oh, I see what you're saying.
Because the bundle of geodesics is the space-time cone, and the space-time cone is quantified by the number of vertices.
Yeah. Right. You're right. Because we could take out the Jonathan claims, because I
like that. Jonathan claims is the euphemism for skepticism.
Right. Well, it just reminds me that I never understood it. Okay. This is also a continuity equation for vertices because each geodesic is basically a necklace of vertices.
Right.
Interesting. Where the proper time, where the graph distance between vertices is the proper time.
Exactly.
Explain to me how that works for things propagating at the speed of light. I mean, this means we have an index going down the path of a photon.
Right. So we have, I suspect, I don't know, but I suspect it may be related to in cosmology when you do things like try and compute the entropy of photons in the cosmic microwave background and things, you have this notion of conformal time, right, where you weight proper time by the scale factor, and that basically allows you, even though it's sort of physically incorrect, it allows you to index world lines of photons and things. I wonder if it's somehow related to that.
It sounds like it. Sounds highly related.
But I can't.
Let's figure that out, because that also might be a connection to the conformal field theory world.
Okay, making a note now. Yeah, it's on my list of things to figure out, but I haven't yet made the correspondence.
All right. Okay. All right. So then, okay. Let's talk about. Okay. So does any of this give the Riemann tensor, or is this all just giving Ritchie type stuff?
Well, so the sectional curvature gives the Riemann tensor. but the
I see. Because in a sense, a way to think about it is, given the bundle, there's a question not only of how it expands and contracts, but also the shape of the bundle. And as you take slices at different angles through the bundle, well, I guess it's just the shape of the bundle, yeah?
right, exactly.
The shape of the bundle should give the Riemann tensor, you say.
Right.
Although formulated as a sectional curvature in some sense.
Mm-hmm. Yes. So in effect, the divergence or convergence of the thing is just giving you Ricci curvature, but the overall
the
structure
shape
of the thing gives you Riemann. Yeah.
Okay, so divergence is Ricci tensor, Ricci tensor.
Right.
Why is it the tensor?
Because it's at least partially direction dependent.
Right. Depends on, is Ricci tensor dotted into the direction of the geodesic bundle?
Exactly. Yeah.
Okay. The shape of the bundle cross section gives the Riemann tensor. Yeah, I agree. Now, the commutator, okay, so let's look at parallel transport in this context.
Okay.
Is parallel transport just following one of these bundles of geodesics?
Yes, I think so. That's certainly one way to think of it. Yeah.
And I mean, the construction of these rectangles seems at this point irrelevant to this derivation, because we can get the Riemann tensor directly from looking at these bundles.
Right, exactly.
Seems more robust.
Exactly.
Okay, now the big thing. Okay, so the claim is made that general relativity, the statement that, which is the statement that the divergence, that the Ricci tensor is 0 in the absence of what we could call matter.
Mm-hmm.
In other words, that the bundle of geodesics does not change size as you propagate it.
Yes.
I.e., vacuum Einstein's equations to the statement that the bundle of geodesics change size. Okay. All right. Great. Let's talk about the higher order corrections then.
Mm-hmm.
So given a particular one of these networks, it's, by the way, not self-evident that this result is correct. I mean, this result will typically be correct for one of these very simple grid networks. Is this result correct?
The result about the vacuum Einstein equations?
Yeah.
It ought to be, yes.
And it doesn't have any kind of sign of a grid. Doesn't have any kind of so given any slicing, right? Let's imagine you just have a square grid, which is what a bunch of these are, right? Mm-hmm. That implies that there is a slicing of the square grid. For any slicing of the square grid, that a bundle of essentially sort of number theoretic paths through that grid at any angle it does seem intuitively reasonable. I mean, you're basically taking this grid. It does seem reasonable.
Yep.
To say that. Now, Okay, so what would violate that? Well, there are plenty of things in these networks that would violate that. So what would a dimension change do?
Dimension change would, in most cases, violate it.
Hmm. It'd be nice to have an example. I think I do have some examples here of things that have one dimension on one side and one dimension on the other.
Okay, yeah, we should definitely test those because I'm pretty sure that it will. Well, actually, no, that's
It's
not
got
quite true.
it's like a it's there's a thing that looks kind of like a pipe that has a I don't know if
Oh,
I
I
can,
think I saw this one. Oh, I saw a predecessor of it. And I remember you had some things that were like spheres with tubes coming out of them and things.
yeah, that's kind of what this thing is. Might take a little while to find. Actually, I wonder what that guy actually is.
One thing I was thinking about earlier today is whether this effectively gives us potentially a way of optimizing Dijkstra's algorithm for certain types of graphs that have, a certain homogeneity property. Because if you're trying to solve, the all pairs shortest paths problem, you can infer things about what the structure of the paths have to be for one region of the graph based on what they are in a different region.
Yeah. Oops. Oh, I see what you're saying. Oh, it's very similar to the previous one. Wow. I don't know why they have that weird boundary in the middle. It's really weird. Oh, look at the arrows.
Hmm, that's pretty cool.
The thing that's always fascinating about these things made by simple rules is that they always make sense inside, so to speak.
Right.
They don't do something just totally, by the time you can see regularity, that regularity will have a way of working itself out.
Right.
Um, um, okay. In any case, so what were we saying here? So we're okay. So we don't. So what do you mean by the next order correction?
Right. So if you now think of this n sub r thing as being, the distribution function, as you can think of it as a distribution function for geodesics, but I actually think it's more instructive to think of it as a distribution function for nodes within the causal graph.
Okay.
So just as you take the one particle distribution function in Chapman-Enskog theory, and you f, and you say that it's f naught plus epsilon f1 plus epsilon squared f2 and so on, and f naught is basically the Euler equations, and f1 is basically the Navier-Stokes equations. We can do the same thing. We can introduce something analogous to, I guess, a Knudsen number or something in for this distribution function, where it's basically allowing n sub r to change. It's allowing that function to smoothly interpolate over different distance scales. So you're saying, you introduce some epsilon where,
Okay, hold on.
Yeah, sorry.
Hold on. We've got multiple things going on here. So first point is the claim. Okay, so hold on. We've got the claim n as distribution function. Okay.
Mm-hmm.
So the first claim is that n sub r is the analog of a one-particle distribution function.
Right. Or there's, I mean, yeah, right.
Okay, so I would like to understand for a second what's the BBGKY hierarchy, the Liouville equation. What is the analog of the Liouville equation here? So in other words, in the treatment in transport theory, there's a Liouville equation, which is the equation in phase space for the whole thing.
Right.
Right, and then the BBGKY hierarchy is the breaking down of that in terms of one particle distribution functions, et cetera, et cetera, et cetera. Right. Now, that assumes some kind of ensemble weirdness, which we don't have. But I'm trying to understand the relationship between this and mean field theory.
Right. Yeah, sorry, go.
No, the assumption that you can get anywhere with a one particle distribution function. So the question is there an equation effectively for the development of n as a function only of neighboring n's?
Right.
Right. So mean field theory is n depends only on n's, right? Which is basically a statement about uniformity, which is roughly a uniformity / randomness statement about the graph.
Right. Yeah, that's a good point.
Because without that, you're kind of toast. You can't really say much at all.
Right. What I think is implicitly proved in the way that I've handled it here is that as long as your causal graph is, as long as it tends asymptotically to a fixed number of dimensions, one has the required level of uniformity.
That was what I claimed in the NKS book.
Well, I think I have a way of proving it.
Good.
Because effectively the ability to do this decomposition, is related to the fact that the Einstein equations are satisfied in the continuum limit. In the sense that I think if you have the Einstein equations, it's quite easy to do this decomposition, right?
Which decomposition? This decomposition into n and its higher order and the higher order n's and so on.
Yes. Because it's kind of like you already know the Navier-Stokes equations at that point.
Yeah, okay, but still, okay, so again, let's go through the higher order, what it means to have a higher order correction.
Mm-hmm.
Okay. So the statement of, what is the statement of, the statement of general relativity is the cross-sectional area of a bundle of geodesics is unchanged in the vacuum.
Right.
Okay. Okay, what's the statement of special relativity?
It's that, okay, so in this context, it would be the bundle of geodesics remains uniform, I think, throughout the entirety of spacetime.
Well, you're saying the bundle in first order. Okay, so special versus general relativity. Okay, so special relativity, consider a bundle of geodesics.
Mm-hmm.
Okay, so special relativity would okay, so special relativity says
All
the bundle is
of
unchanged.
Yeah, throughout all of space and time. It's always a, a times t to the n thing.
What's a times t to the n? What do you mean?
That would be the sort of vertex distribution function for zeroth order sort of special relativity causal graph. That's just giving you the
By the
volume
way,
of the
I mean,
spacetime.
my view of the, yeah, I mean, one thing that is troubling me a little bit is when I talk about a bundle of geodesics, my initial view is a spatial bundle, but this is, of course, cones of geodesics.
Yes. Yes. Which are slightly harder to think about.
Okay. Bundle is unchanged through space-time, i.e., which is essentially the statement of the invariance of the speed of light.
Yes. Yes.
Okay. So GR is the statement the bundle has a fixed area, fixed cross-sectional area.
Mm-hmm.
Okay. What's next? So one thing is to say, so what are the feature of the bundle? So in a sense, general relativity is making a more precise statement about this bundle than, well, there are two different things. One is a correction to general relativity, in which it says actually the cross-sectional area isn't fixed. And the other would be an additional constraint that says that something else is true about the bundle of geodesics.
Mm-hmm.
Right?
So I think in the Chapman-Enskog case, it would be the constraint.
Okay, two directions. One, additional constraint on the bundle, or two, corrections to, e.g. the GR interpretation.
Well, actually, no, sorry, it's not true. It would be both. Both are possible.
Okay, well, so the second one certainly will happen if dimension changes.
Yes. But I mean, so the Burnett equations, you can think of them as, I mean, they're a superset of the Navier-Stokes equations, right? You can simulate the Navier-Stokes equations with them, but you can also correct them.
Okay, let's take a look here. So
I think what's happening here is fairly analogous to what's going on in the hydrodynamic case. It's just that instead of the Ricci tensor, which is giving us the divergence of these geodesics, in the hydrodynamic case, one has the divergence of the Cauchy stress tensor for the general continuum equations for first order.
Look at that. That's an SMP program.
It's kind of cool.
Well, at least we could do the same thing. Terms in the Chapman-Enskog expansion. Okay. Someplace here. Okay, I'm just trying to remind myself how this works. Okay. So there's a notion of equilibrium, which we sort of have, but we don't really have, but we sort of have that.
Mm-hmm. Well, equilibrium is just SR.
I don't think so. I think with these actual networks, it's going to be equilibrium is just the randomness where statistically N of R, okay, so equilibrium of space-time, right, is that N of R is statistically stable.
Okay. Yeah. Well, I mean, right. So SR is certainly a sufficient condition.
Absolutely.
Yeah.
Absolutely. But it's a very much extreme. It's an extreme condition
right.
that just says space-time is totally boring and nothing's happening in it.
Right. Okay, interesting. So that is if yeah, right. That is a deviation from a
Absolutely.
hydrodynamic case.
Which?
This notion, right? Because if SR is the zeroth order approximation, then I
Well,
was
look,
assuming that would
no,
be
no,
formally analogous to the Euler equations, but the Euler equations
it's
are
not.
identically the equilibrium case.
No, 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 that's not the case. You can get the Euler equations, even if your particles in this setting, in these things, okay?
Mm-hmm.
Even if the particles do just totally trivial things, you still get the Euler equations.
Right.
In other words, you don't need randomness to get, don't need particle randomness to get the Euler equations.
Mm-hmm.
Even if the things are going around in platoons all over the place, you still get the Euler equations.
Okay.
So I think it is analogous, directly analogous to special relativity.
Fair enough. Okay.
This is really cool, I have to say.
Hmm.
This is really cool. I mean, this is very beautiful.
Hmm.
Now we just have to get, spin statistics and quantum field theory, and I mean, nothing's ever worked like this before. None of these theories have ever been able to, beyond just putting stuff in. Okay, so here, this is the Chapman-Asco expansion, according to my, let me just remind myself of it. Okay, so the basic thing is it's an expansion in powers of velocity. Okay, so N of A is, N of A is the number of particles. F of A is the distribution function that says, so this N, which is what the continuity equation applies to here,
Mm-hmm.
I think that could simply be, okay, I claim a trivial version of this analogous to particle look, in these pictures, okay, there's no branching, right?
Mm-hmm.
Well, actually there is branching. Not completely clear on how that works. Okay, but anyway, let's come back to Chapman and Skog for a second. Okay, so my claim here, the first three terms represent the change in microscopic particle densities as a consequence of changes in macroscopic fluid velocity.
Mm-hmm.
Fourth term accounts for the first order dependence of particle densities on the macroscopic spatial variations in fluid velocity.
Right.
Okay, so what's the analog of any of those things? Because your statement about collisions isn't quite right. That's going from the collisionless Boltzmann equation. The Boltzmann equation has a big collision term in it.
Right. But the point is, you can define an integral. All that you're really dealing with when you're talking about collisions is some nonlinear integral operator. Right?
Yes.
And you can define a nonlinear integral operator for hyperedges, effectively.
This puppy here is the energy momentum tensor, I think.
Oh, cool. Yeah, that looks right.
So the claim here is that the form for the energy momentum tensor follows from the Chapman-Asco expansion.
Yes.
Okay, the thing I'm trying to look through here is then well, it takes a little bit of thought there, but what I'm looking for, okay, higher order corrections. Okay. Okay, so these are the higher order terms, for what it's worth, in that Chapman-Asco expansion. The hell is that? So that, you know what that is? So the Riemann tensor is a particular moment of the shape of the geodesic bundle. Okay, this is a higher order, this is the higher order spherical harmonics of the shape of the geodesic bundle.
Right.
Okay, so analog is looking, and in fact, that I remember in this derivation that the different orders of tensors is looking at the higher order tensor shape of the geodesic cross section. CF spherical harmonics. Now, for example, in this case, okay, so here, okay, so for what it's worth, that's what the higher order correction to the Navier-Stokes equations looks like in this case.
Right.
I see it has contractions of 3 velocities and 2 derivatives. And look at that, here we have tensors. That's an interesting thing. That's the isotropy condition on the tensors. What's the analog of that here?
Yeah, I don't know. I mean, we have a discrete line element. We can define a notion of isotropy. Whether it corresponds to the notion of isotropy that's used here, I don't know.
Okay, but anyway, I think we just figured out what the form of the
higher order corrections will be.
Yes.
Yep.
So the form of the higher order corrections will be to look at, okay, the next moment. So it's not tidal forces, the next moment of the shape of the geodesic bundle.
Right.
So the first thing is quadratic forms, I think. The next thing will be quartic forms, probably.
Right.
I don't know if cubic ones are possible.
I mean, they're certainly not in.
I understand. Are cubic terms possible? Are R log R terms possible? And is that what a dimension change would do? In other words, okay, you're measuring the shape of the geodesic bundle and you go through a dimension change. what happens to the shape of the geodesic bundle? What is the first order correction to the shape of the geodesic bundle?
Well, the radius, if you increase the dimensionality, the radius will increase.
Okay.
Right.
So that's a violation of, that's even a special, that even seems like a special relativity violation. Well,
right. Well, no,
no,
not
it's
if
not
the
clear.
dimensionality changes uniformly.
Fair enough. So, okay. What is the signature of dimension change? In the geodesic bundle? And what does it mean? So my claim about making dimension a dynamical variable, in a sense, the Riemann tensor is a dynamical variable.
Mm-hmm. Right.
I think there should be simply an equation for, you know, this geodesic bundle cross section. Let's see, in terms of yeah, there should be an equation that depends on in which dimension enters as a variable. I mean, it doesn't just say R mu equals 0. It says something that involves dimension. So the analogous statement, look, the analogous statement for small dimension change is it's R to the D times 1 plus R squared times the Ricci scalar.
Mm-hmm.
The corresponding statement, actually, there's a couple of horrifying things here. Okay, is dimension a scalar? That is an important question because not obvious, right? In other words, you could imagine a case where the dimension is increasing in some directions and not in others. In fact, I don't think it is a scalar. I think it has perfectly, you know, we could take apart n sub r and look at different directions. You know, for r, right? It's an assumption that r is isotropic.
Right. I mean, obviously, in general, the dimensionality will have the same algebraic structure as the Ricci tensor, one would expect.
Let us ponder that question. Let us ponder that question. Remembering that the Ricci tensor has a number of components that depends on dimension.
Right. But you could also have a dimension tensor which has components that depend on the Ricci tensor or the Ricci scalar.
Well, Ricci scalar is a lot easier.
Right. Because what's really happening here is, okay, so if you have some arbitrary metric space, you can define a sectional curvature on that metric space using the notions of unit speed geodesics and things. Because effectively what you're doing is you're just taking, you're defining some you're defining a surface that's really just the tangent plane given by a pair of unit speed orthonormal geodesics, and you're computing the Gaussian curvature of that tangent plane, and that's a notion that extends to an arbitrary metric space.
Okay.
So then what you can do is, so once you have the sectional curvature, the way that you get the Ricci curvature is you just take you take the sectional curvature, which is a function of these two vectors, and you just compute the average of the sectional curvature over all possible vectors for the second argument. And but the point is that in the final step, you weight the whole thing by the dimensionality, right?
You mean in the formula for the formula has a d+2 in it?
Yeah, right. I mean, ultimately, what you end up with in the second order term is epsilon squared over 2d+2. But the reason you get that is because when you do this averaging over the sectional curvature, you weight the whole thing by dimensionality, and that gives you the coefficient.
Let
Right.
me understand that. So when you weight it, so what you're saying is you're looking at all possible directions.
Mm-hmm.
Were you not to do that if you only had one direction to look at?
Yes.
I need to understand this more, but what you're saying is that okay, I'm sorry. Let's zoom out again for a second. Okay, so the question is the dimension tensor.
Yep.
What is the dimension tensor? How many degrees of freedom does it have?
Right.
Okay. So in general, you have to go smoothly. I mean, this is where the number of degrees of freedom. Okay, hold on. So your point is, think about it in terms of bundles of geodesics, and that's the true thing. That's the ground truth.
Yes.
Now, these are various characterizations of the properties of that bundle of geodesics.
Right.
And how does that work? We're getting close here.
Mm-hmm.
This is where we're getting close. Okay.
Right. So my point is that when you do this averaging process, another possibility is that you weight the whole thing by a fixed Ricci scalar, and then that gives you.
Okay, I need to understand some basic things here. I don't understand what sectional curvature is, so let me start with that question. I'm sure I've known this at some point, but let me just.
Right.
See. I love that the sectional couch is the first thing that shows up. Okay.
Right.
Oh God, Wikipedia is so frigging technical.
For some things.
I wonder whether there's a
Right. I mean, so all that's happening is you say, okay, take two orthonormal tangent vectors.
Okay, hold on.
Right?
I'm going to write myself some notes here. So this is sectional curvature.
Right.
Okay. So two orthonormal vectors.
Right. I mean, they can just be tangent vectors, but if we make them orthonormal, it's easier.
Okay.
So they obviously define a two-dimensional plane in the tangent. If they both originate from a common point in the manifold, then they define a two-dimensional plane in the tangent space at that point in the manifold.
Yeah.
Okay. So then all the sectional curvature is the Gaussian curvature of the surface which has that plane as its tangent plane. And that surface.
The Gaussian curvature of the plane. Okay. And the Gaussian curvature
Okay, here's a better way to explain it, arguably. So those orthonormal vectors define this two-dimensional plane. You can now think of, okay, look at the set of all geodesics which start at that common point and which have directions defined by that plane. If that makes sense.
But by the way, I'm sorry, just some very basic thing. Gaussian curvature is about kind of fitting spheres to things. True statement?
Right, yes.
So okay, it's the product of the principal curvatures. Okay, so imagine fitting a sphere at a particular point. Well, in general, an ellipsoid.
Right.
So the Gaussian curvature depends on the geometric mean of those curvatures, yes?
Mm-hmm.
Okay. All right. So let's come back to your statement about. Go ahead. What were you saying?
Yeah. So we have we have a point on some manifold, and we take two orthonormal vectors emanating from that point. So now we have some tangent plane, and then you can say, okay, let's take the space of all geodesics that emanate from that point and which go in the directions defined by that tangent plane. Right. So you know i.e. the geodesic, the origin of the geodesic is that point, and the initial direction of the geodesic is the direction of the tangent plane.
Wait a minute. The tangent plane is defined by two. Okay, given two geodesics emanating from a point. That defines a plane.
Mm-hmm.
Why are you calling it a tangent plane?
So we're not at the plane is for the tangent vector. The plane is defined by the tangent vectors. We haven't got to the geodesics yet. So you take a pair of tangent vectors, and they define a tangent plane, or they define a plane in the tangent.
But we don't have any vectors. In our networks, we don't have vectors. We just have geodesics.
Yeah. Oh, sorry. Hang on. Yeah. So I'm defining an orthonormal, I'm defining a unit length vector to be any hyperedge.
Okay. Hey, I just need to get a piece of food, otherwise my brain is going to shut down here. Just 1 second. I'll be right back.
Okay.
Okay. Right. Okay, keep going. What were you saying?
Right, right. So we have some notion of tangent vectors in this.
Which I'm not understanding, which you're just saying it's an arbitrary hyperedge.
Yes. So we can say, so in,
Okay,
you know,
so Jonathan's claim from a given point, any set of hyperedges can be thought of as tangent vectors.
yeah, any set of non-parallel hyperedges. So as long as they're not incident on the same vertex set, they can be thought of as orthonormal vectors.
As orthonormal tangent vectors.
Right.
Okay.
Okay. So given a pair of orthonormal tangent vectors, we have a plane, we have a tangent plane. So then what you can do is you can say, let's start at some point, and then, you know, obviously that plane defines some infinite set of possible vectors. And then you can say, let's start at some point and let's just set a geodesic going, emanating from that point in the direction of a vector in that plane, the initial direction. Right, so then we have that defines a space of such geodesics, which is some surface. And then you can ask, what is the Gaussian curvature, the product of the principal curvatures of that surface? And that is the sectional curvature.
Okay. I think we need to deconstruct this a little bit more. Okay, so got a bunch of these tangent vectors. So imagine in one of our pictures here, we pick from one of these nodes, we just pick, you know, random edges here and here. I don't know whether the arrows do matter, don't they?
Yes, right. They have to be directed.
Okay. All right, we pick a couple of these vectors, wherever. I mean, there are only two available here. Okay.
Right.
Okay, then what do we do?
Right. So if this were a normal Riemannian manifold or something, then we'd define we'd use that to define a plane.
But by the way, I mean, I'm sorry. There's an arbitrary path. I mean, are you talking about just one? We don't get to define a plane here because you just told me about two links. Are you imagining that you keep going from those links?
Yes.
How do you know whether you're going in a straight line?
Right. So the definition I was giving you earlier is the intuitive geometrical definition for a Riemannian manifold. There is this less intuitive, discrete version that Olivier came up with, for which I don't have a straightforward explanation.
What is it?
So the idea is, what's the most efficient way of saying this in words? So you have two, unit length geodesics, which are just hyperedges in your network. And then you consider another pair, which you can, that's sort of a small distance away, that you can think of as being, like the mapping of the first pair under some parallel transport operation.
Okay.
Okay. So then what you can ask is, okay, then what you're doing is you're taking the ratio. Okay, so the intuition is just as the Ricci scalar is giving you, one way you can think about it is that it gives you, if you have two balls in the hypergraph that are close by, such that one is kind of, you think of the points on one as being parallel transported versions of the points on the other, it tells you the ratio of the volumes of those balls. In the same way, the sectional curvature is telling you, if you have these two pairs of tangent vectors that are both emanating from a common point in each case, it tells you the ratio of the average distance between the endpoints of those tangent vectors to the distance between the common points, if that makes sense.
Not quite. I lost it at the last moment.
Okay, right. So you pick two. Okay, so let me talk exclusively about the hypergraph case. You pick two vertices in this hypergraph, P and Q,
Mm-hmm.
and then you take. So actually, you don't. In the hypergraph case, you don't even need a tangent plane. You can actually just pick one hyperedge because there's a symmetry argument. So what you can do is let's just pick a hyperedge coming out of P and a hyperedge coming out of Q.
Okay.
And then you can ask, what's the ratio? And those hyperedges will have endpoints. And you can ask, what's the ratio of the distance, of the shortest distance between those endpoints to the distance between P and Q? Right?
Okay, so wait a minute. Okay. So this is about defining sectional curvature.
Right.
Okay, so we got 2 points, given points P and Q. Consider edges coming out of P and out of Q.
Right.
Look at the endpoints of those edges. Ask how far apart, how geodesically far apart are P and Q,
Right.
and how far apart are the endpoints of following edges from them.
Right.
Okay, I understand that.
Right.
So following a single edge, you're talking about following a single edge.
Precisely.
Okay.
And so
I'm very scratchy at the level of single edges. I don't really like following a single edge, but anyway, okay.
Right. So then the point is that this ultimately depends on two vectors, right? One, the vector coming out of P, and the other, the vector coming out of Q.
Sure.
And so this is the notion of a sectional curvature on a hypergraph.
Well, where's the curvature?
The curvature is the ratio.
Okay, hold on. So your claim is curvature is the ratio of the distances between the endpoints of the links from P and Q and the ratio of the distance between the endpoints of the links and the distance between P and Q themselves. So what do we call distance? We hope we won't call it D because we've already got a D for dimension.
Well, yeah, I've been calling it D and using N for dimension.
Oh God, don't do that.
Okay.
I mean, I think if we want dimension to be a dynamical variable, it better be lowercase.
Right.
Could be capital D.
That could work.
That's a possibility.
Doesn't get confused for a differential operator.
Well, let's assume those are all Russian Ds of some kind.
Right. And so,
Okay,
so
so
then the nice thing about the sectional curvature as defined there.
okay, so let's say P prime Q prime divided by dpq, right? Okay, so what is that? So that's so we can compute that. I can obviously easily explicitly compute that for any of our graphs.
Right. Right.
Now, then you say you average that. Oh, I see. I see. Averaging over all possible orthonormal quotes, orthonormal. Okay, I see how this is going to go wrong. I've got a fix.
Okay.
Normal vectors gives a factor d because that's the number of orthonormal vectors.
Yes.
Okay. So let's look at that. So
in effect, when you average over one set of vectors, it gives you it gives you something related to the Ricci tensor, and when you average over both, it gives you something related to the Ricci scalar.
Well, where's the averaging happening at all? I mean, the averaging is with respect to points P and Q.
No, with respect to the hyperedges that emanate from P and Q.
But you're saying if you don't do the averaging, look, okay, this is the same definition, isn't it? I mean, it's the, okay, so our normal definition of Ricci tensor okay, given 2 points P and Q, they define a geodesic between them, right?
Right.
So our normal definition is that the curvature is associated with the growth rate in the number of points you reach in that tube.
Yes.
Okay, so here you're doing something which I think is wrong, which is to look at the single link result. I just think that's.
Well, I mean, there is a more generic way you can do it, right? You can look at you can look at a geodesic. I'm trying to take the limiting case where the geodesic is of unit length.
Oh, but okay, but you're looking at a geodesic to random place X.
Yes.
So in a sense, you're defining them. Okay, so that in fact looks a lot more like the Riemann tensor definition, because what you're doing then is from P define a geodesic to P plus or something. Okay. Then what we're asking is to compare the distance between P and Q yeah, I mean, isn't this just exactly a Riemann tensor rectangle thing? Because you're looking at the distance between P and Q.
It is up to an inner product of the vectors. Yes.
Okay, let's go through that. Let's again. So you're saying what exactly is the claim about curvature? So I mean, I don't think it's going to work with single distance links. I think it's just going to give nonsense.
No, that's fine. Yeah, I was just trying to take the limit case where in effect P and Q are separated by a single hyperedge, and you only go out a single hyperedge. But in general, it works for any small distance.
All right, fine. But I mean, so we've got okay. So walk me through what exactly the math is. So we've got D of P and Q. We've got D of so define a geodesic to P plus. So that's then the end point.
Yes.
I was just what I was calling P prime before.
Right, right.
It's easier to type. Okay, geodesic to P prime and a geodesic. So we're going from P, we go to P prime, from Q we go to Q prime. Then we ask ourselves, for all possible geodesics of a given distance, okay, for the whole ball of geodesics, for all geodesics of a given length, what is the ratio, this ratio here?
Right.
And what does that give you?
So that gives you 1 minus the length squared over 2 times the sectional curvature plus higher order terms.
1 minus length squared over 2. Length of what?
The length of the geodesic.
Of a given length. So you're scanning out from that point.
Right.
Length geodesic over 2 times sectional curvature.
Right, which is usually denoted with K.
All right. Okay, I don't understand this. I don't understand this. That works in any number of dimensions?
Yes.
Okay, the ratio of those two things. Well, we can obviously compute those. So that ratio, the claim is that that ratio, the first order term in that ratio is L squared.
Right.
Although there are clearly higher order terms. Actually, that's obvious because it couldn't depend on L.
Right.
Okay. All right. So that's another definition. Okay. And so the claim is that that is closely related to. Okay.
It's a slight algebraic rearrangement of the Riemann tensor, but it's basically this. It's measuring exactly the same thing. It just happened. I don't know precisely.
But there's only one sectional curvature here. There's only one scalar sectional curvature here.
Well, so you've done effectively this averaging over all geodesics.
Okay, so given two particular directions to P prime and Q prime.
Right, you get a particular sectional curvature.
Given those two vectors.
Yes.
Okay.
So that gives you a sectional curvature.
Okay, and what does this have to do with anything here? What was this? I mean, so why did we get to this? We
were trying to define some notion of parallel transport that worked in hypergraphs. So we
were trying to work out the generalization of this question of is dimension a scalar?
Right.
Okay.
Right.
So this derivation doesn't depend on that. L squared over 2 is just the integral of x from 0 to L, isn't it?
Right, exactly. So the point is dimensionality hasn't appeared yet. Right? But dimensionality does appear when you start dealing with Ricci curvatures. And the way that you get the Ricci curvature, well, because in the way that this is conventionally done for metric spaces, and therefore by extension for hypergraphs, one actually kind of bakes in the dimensionality directly. Because what you do is you say, we define, one way you can define the Ricci curvature along a vector, along some vector u, is that it's the average of the sectional curvature of u comma v over all vectors v.
Right. Okay, so then, dimension enters because you average this quantity over the possible relative directions
Yes.
of P prime versus Q prime.
Mm-hmm. And as you say, of course, that that's determined by the weighting of that average is determined by the dimensionality of the manifold.
Let's think about in our case. Okay, average this quantity over the possible relative directions. So in effect, what we're asking is, see, the thing I'm not quite understanding, we've got a ball, and what we're effectively asking is, how much of the ball does each individual geodesic P minus P prime, Q minus Q prime account for, I think.
Right.
But I don't quite understand the cardinality of that statement. Right, because in the usual case where we have dimension, we know that those are degrees of freedom. What's the analog here?
Well, it's the analog is some average of the number of non-parallel hyperedges emanating from each vertex.
That's the volume of the ball. Think about the surface of the ball, right? The number of non-parallel hyperedges is the number of hyperedges that are incident on the bounding surface.
Right.
Okay, so what's your point? So you're saying, I see. So given a particular, this isn't right in terms of cardinality. Okay, given a particular P prime, comma Q prime, imagine them as points on a sphere. Okay.
Okay.
You've got two particular P prime and Q prime, but you've got all the other points that define the the 4 pi r squared of area on the surface of the sphere.
Right.
Now explain what you're talking about in terms of this averaging.
So the issue is the continuous case is so different to the discrete one. But
you understand my cardinality problem. I think that what has to happen is, I think what it's going to be, okay, is the comparison between that plane that you're sweeping around, that's both the joint PQ thing versus a single line being swept around.
Right.
That's what I think it's going to be.
Right.
So I think it's the comparison between the 1-point function that defines the total area, the total volume,
okay,
area of the bounding region, versus the 2-point function with which defines what now. So you've got these 2 points. Okay, let's think about this. They're sweeping all over the place. How do they I think you're counting. Okay, here's a claim. Which counts the number of lines of a given length on the area. Okay, so the idea would be, one thing is, do you get the idea? So I mean, what we're saying is, imagine you've got this sphere and you're counting one thing is just the mesh. I mean, I've got some nice spherical meshes. We should look at this. One is the number of mesh points. And the other is the distinct number of mesh lines of a given length in that mesh.
Right.
So imagine you have a square grid.
Mm-hmm.
And you're doing Manhattan distance or whatever.
Right.
Yeah. Something like this is going to work. Think about it. So think about a region, an n by n region,
mm-hmm.
right? Okay. In an n by n region of a square grid, there are, needless to say, n squared points.
Mm-hmm.
How many geodesics of length L are there?
Right.
Okay. So that's an elementary combinatorics problem.
Mm-hmm.
But what's the answer? We could compute it. That is super embarrassing that I think we have to compute it. It's a grid graph, right? So in what we've got is a okay. So now what we're looking at is how many paths of length L are there on this, right?
But not paths, geodesic paths specifically.
Yes, how many geodesic paths, right?
Which is harder to solve. I mean, like the paths thing, I think we can solve quite easily. But
Well, aren't the geodesics here just straight lines?
yes.
Well, actually, they're straight lines with one Manhattan turn. So they are. No. Every one is the same length, isn't it? I mean, given to get from here to here, right? It's just a count of the delta x and delta y. So given delta x and delta y, the number of distinct paths is just, you can, at every x and every y, you can choose to.
You can choose two things.
Right. So is it 2 to the x plus y?
Something like that.
Otherwise known as 2 to the L. So given.
Can it be that simple?
I think it is that simple.
Okay.
Given. Okay. So the number of geodesic paths length L is to the L here. Okay, that's a little odd because that's saying that that's exponential. And I don't see any place where a logarithm is taken here. Counts the number of lines. Do you agree with my interpretation of the way that what this is doing? I mean, it's either counting the number of single things or it's counting the number of geodesics on that surface. Do you agree that that's a reasonable, that's.
I mean, that might be right. I don't know.
And there are exponentially many more geodesics because, okay, so to cut the number of geodesics down to scale, why the hell is the number of, I mean, so in the usual, oh gosh. Okay, given a manifold, right? The number of points, I don't even know what the number of points means.
Some volume measure.
Yes. And how does the number of lines relate to the number of points in a manifold? Is it exponentially related or is it somehow linearly related?
It ought to be exponentially related.
I
Because
see. Given one point, you've got to pick another point.
yeah, right.
But why isn't that just the square of something?
Because you also have to pick points in between, so to speak. That if you have some metric space and you have a pair of volume measures, the number of possible transportations between those volume measures is exponential.
Okay. All right. Listen, I think this is the right intuition about
Okay.
one is a 1-point function, the other is a 2-point function. And my prediction is that the 2-point function is like slicing with a plane, and then you're going to compute essentially the non-directness, which is going to give you the curvature when you slice that way. And that, in effect, what you're doing by doing that, this thing about fitting, you're fitting up an osculating ellipsoid, so to speak, to the thing, right?
Right.
But you could imagine, fitting an osculating degree 4 surface if you wanted to.
Yes. Yeah.
And I claim that will be related maybe to the 3-point function.
Mm-hmm. That sounds plausible.
What's also very interesting about this, the name 1-point function, 2-point function was not chosen completely frivolously.
Mm-hmm.
Because it reminds me a lot of what happens in conformal field theory and so on.
Right.
And the Feynman diagram, the large N expansion interpretation of all these things.
Right.
Well, that would be just too much unification for one day. If it turns out that these, yeah. All right, I should probably get back to what I was doing, and you should get back to. But I think, the one thing we were going to do was the what their names, the meshes.
Mm-hmm.
We could perhaps tackle that tomorrow if you're up for it sometime.
Yep, sounds good. So this is the Schwarzschild metric stuff.
Right. I am. Let's take a look. There's some technology there that this is using. Let me just take a look. Oh, those are geodesics.
Yeah.
That's one of them in the wild. It doesn't look very straight here, but so it goes. Where is this? Why didn't I call it geodesics? The heck did I call it? Dang. Hey, another thing that we have not looked at is the weighted multi-way systems.
Mm-hmm.
Did you have any? We're changing topic totally, and we shouldn't do this. But did you have any thoughts about that?
Yeah, so I need to work out the details, but I think there is something here about, summing of amplitudes for these things that, weightings of different parts of the causal graph are basically just amplitudes of different states. But yeah, I need to work out the precise details of how that's going to work. But I would like, if I do end up writing this, quantum mechanics paper,
which you should, yeah,
which I should, I hopefully will have the details worked out.
You don't have to have the quantum mechanics pre-launch. I think if you do have it pre-launch, it's fantastic, but I don't think it's necessary.
Right. Well, I mean, at the very least, I'd like to have, even if it's not a complete paper, at least a note that says something about these completion ideas and notions of commutativity.
I mean, listen, at a very basic level, when this launches, you should make sure you give some talk in Cambridge about it.
Right. Yes. Well, I've already got a couple of people in my research group kind of interested, and so I can do some wider advertising and give a seminar.
Right, but you should give. We'll surely we can arrange for you to give some talk about this.
Right.
But
and actually, speaking of which, of the people I've managed to get interested by just talking to them about it, a couple have already expressed an interest in coming to whatever it is, the 2020 summer school.
Excellent.
If there is a possibility of working on this stuff.
Well, there will be, of course.
Yeah.
There will be.
We should discuss at some point exactly how that's going to work. But
yeah, well, I mean, it'll just be some proboscis of the summer school. I mean, I don't think it's clear there's no structural problem with working on physics there. We'll just have to have a physics track, and have different. I mean, Matthew Sudzik can still give his talk about combinators for that track.
For what's the nth year now?
I think it's like 18 or something. So,
I would go crazy.
Well, he has a different personality, right? It's but okay, but let's just come back to this weighted thing for a second, okay? So, why are complex numbers important for amplitudes? Really what it is, it's the way that probabilities combine. So in other words, the naive way probabilities combine is you have one path and then you have another path. You get to one point, it has a certain probability of getting to that point. The probability to get to the next point is just, P1 times P2.
Right?
Okay. Oh, look at this. So you know what? Think about a multi-way system, right? I'm trying to think about a multi-way system in which there is some combining of states beyond just identicality, so to speak. So in other words,
like isomorphism.
Yes, but even beyond that, I mean, I'm trying to think. You're going from A to B in the well, let's think about it in terms of causal graphs. So we got the multi-way causal graph.
Right.
In which every possible, and for causal invariance, every possible slice of the multi-way causal graph is isomorphic. But let me see. I'm asking the question, given you go from A to B in these two probability, when we talk about probabilities, we're averaging over all kinds of stuff. So the point is that somehow that averaging doesn't work, isn't a pure probability averaging, because somehow look. The question is, what does it mean to be at a particular state? And if there's a whole equivalence class of states, it's much less obvious that you go from, probability of a transition from 1 to 2, probability of a transition from 2 to 3. And how does that compare with the probability
Right.
of 1 to 3?
So the intuition is that it's like complex numbers give you an equivalence class of classical probabilities.
Well, you're saying when we think about that in terms of amplitudes,
Right. There are many possible complex numbers that give you a certain norm squared.
yes.
So in effect, what you're doing is you're modding out by some equivalence class of states.
Yes.
There's something to that.
Well, in general, what you're doing is you're taking a sum of the products of the amplitudes, right?
Mm-hmm.
There is something to this. There is some way to get this.
Yeah.
Oh, well, if we can get that, okay, we've only got spin statistics, particles, and, a few other things. I mean, the thing that's very interesting about all this stuff is we're not yet running into horrible computational irreducibility.
Yes.
None of the stuff would.
Yeah.
Yeah. Go ahead.
I wonder if that's that's indicative of the kinds of things which mathematical physics has conventionally concerned itself with.
Definitely. And it ain't going to give them muon mass, is my expectation.
Yeah, well, right. Yeah, I mean, so yeah, I guess the converse is that the things that currently do not have elegant mathematical explanations will probably correspond to things that are computationally irreducible in some way.
Yeah, I'm sure that's correct. Things for which there is an elegant theory will not be full of this particular combination of hypergraph rewritings happens to lead to such and such.
Right, right. They will be much more general features of these systems.
I'd like to get spin statistics. That will be a good test because I'd like to get representation of the Lorentz group, a Poincare group rather, for some way. That seems not completely out of reach. I mean, although, that's an interesting issue.
I mean, it must be related somehow to special relativity stuff that we've dealt with.
Yes, and you know what? Think about SOD for continuous D.
Mm-hmm. Right. I'm already kind of running into this problem with the changing dimensionality stuff because, like I mentioned, I think at least the way I've tried to come up with for thinking about this is extend the notion of a coordinate chart to be a more general covering map, so that in effect, rather than your coordinate chart giving you curvature as some measure of a deviation from the from the underlying Euclidean space, if you now you have some universal covering map, you can think about curvature as being a deviation in the dimensionality from the base space of that covering map.
Mm-hmm.
But then you run into a bunch of stuff about covering spaces and charts of SO3 and things, which I still need to figure out.
Okay, hold on. SOD for continuous D.
Mm-hmm.
I happen to once study this thing in a different. The only thing I know for sure is that the orthogonal polynomials are Gegenbaur polynomials.
Right.
And those are definable for arbitrary D, not necessarily integer.
Right.
What would I look up for rotation group non-integer dimension? Okay. Fractional calculus. Oh. Oh, I remember this guy. I think this is relevant to us.
Mm-hmm. Looks like it.
God, the fact that it's got actual particles in it is crazy bonkers. Oh my gosh. The bad thing is these particles are my personal friends. So it's like when they talk about these particles, I actually know plenty about what they are. Seems like we should probably get this.
Yeah.
You know, Oleg Marichev is a world expert in fractional calculus.
Mm-hmm.
And probably can tell us anything we want. He probably would know. He's not very much into formal stuff like formal group theory, I think, but he probably would know this.
Mm-hmm. Yeah. Worth consulting.
My oh my. It seems like it might be relevant or it might be totally irrelevant. This is the origin of space. Oh, wow, he's got a space evolving. Good for him.
Oh my God.
Well, but that means there's an actual person who's talked about this. It's very recent, 2013.
Okay. Slight concern that this was filed under general physics, but
Fractional quantum harmonic oscillator. Okay, so this is just formal. That seems kind of weird.
Herman at gigahedron.com.
Well, he gets credit though for. Well, okay, but so he gets credit for having at least discussed them. I bet he didn't refer to NKS, but certainly discussed. I don't know. I don't believe in looking at references. It just causes trouble. That name rings a bell. I've run across this character, I think. Okay, but the question is, what is, you know, I think fractional dimension, that would be a useful thing to know, because if we knew that, and we know about the representations of SOD, the question is, how do the representations of SOD play out on a hypergraph?
Right.
Because imagine a grid graph. It has certain symmetries, which are a subgroup of SON. So an interesting question, if we claim we have a d-dimensional thing, are its symmetries a subgroup of SOD?
Right.
See, whenever there's something variable, by the way, in, you know, the crazy lesson of quantum field theory is, whenever something is variable, there will be a particle, a quantized particle associated with its variation.
Right.
So that suggests that in, you know, if dimension varies, there's a dimension in an ion or something.
Right.
which is somehow the carrier of quantized dimension.
Which may or may not be isomorphic to gravitons.
Right.
One would hope that it would be the same.
Maybe it's something different. Maybe there's two things. Maybe there's a, maybe in the first order approximation, which is what particles are, right? There are, it's like if you are living in one of these things that like Max studies in weird supersymmetric models and so on, right? The first order perturbations in one direction are, happy fermions, and the first order perturbations in another direction are happy bosons.
Right.
So it is not the first order approximation. It's not self-evident that two different variations would be the same. I mean, so there might be a graviton and there might also be a dimensionon, which is something different.
I conjecture if it's not a graviton, it will be something more like an inflaton.
Which actually, those are related. Wait a minute. This is after my time in the business. What are those?
So in a sort of standard scalar field model of inflation, the inflaton is the governing boson.
Oh gosh, that's horrible. They introduced a new one. That's disgusting. Back when I was talking about this stuff, it was just the Higgs field. But I guess it can't be the Higgs field because we know too much about the Higgs field now.
Right, it's definitely not the Higgs field. There is are you familiar with quintessence as a concept? Right. So then there are quintessent scalar field models where you have an inflaton that effectively decays into a Higgs field and a dark energy, cosmological constant piece.
Yuck. No, I don't agree with you. I think it'll be something different. I think it'll be something much more bizarre. I think it'll be something. For example, what spin do you think a field that's associated with quantized changes in dimension has?
I don't know.
I mean, the reason that... So I'm going to make a claim. I bet it has continuous spin. I bet it does not have quantized spin.
This is awful. Okay.
That's what I think. And the reason I say that is, in the Poincare group, for example, tachyons don't have discrete spins. I think to end up with discrete spins, you end up having to have quite a lot of structure. Okay, so
bye spin statistics theorem.
Well, it would be a little bizarre for a continuous spin object. Is there a particle associated with quantized changes in dimension? What spin does it have? We need to understand SOD for non-integer, because that, again, that tells us I bet there's literature on it. I bet there's something that's known about it.
Right.
Because we know it's orthogonal polynomials. Are you finding something about it?
I'm looking into it, but it's hard to find literature immediately. I'm also just thinking about, I don't know, I mean, a thing which kind of changes dimensionality locally. Another way you can interpret that is a thing which changes the local speed of light, or the local effective speed of light. Right? Because you're changing the causal structure of the manifold.
Right.
And I'm wondering if there's, I'm trying to get some physical intuition for that.
Well, I don't think the speed of light is a promising thing, because I think that that's going to end up being Ah, okay, so yeah, there's also invariance groups of fractals would be another thing to wonder about.
Mhm.
See, they should be a subgroup of SOD, that any of these things.
Mhm. Only partially related,
Yeah.
but we may be able to start investigating spin statistics like things empirically by just it. We have the notion of what it means. I think at least we have the notion of what it means for an operator to be commutative in these systems. And so if you have some, update rule that creates particles, that creates some form of persistent structure, we can start to look at what, if you have rules that commute versus rules that anti-commute, what's the difference in the persistent structures that they produce?
I understand the claim.
We can start to gain some insight into what spin might mean.
Yes, that would be interesting. That's not a bad idea.
Okay, I might start looking into that just so I can get some intuition for these things.
Too much stuff is working here.
Right.
All right, I better go back to working on the actual text of this stuff because we really got to get that finished. But d-dimensional rotation groups definitely a thing, and the symmetries of these objects definitely a thing.
Right, and I suspect there will be some collision with the scale relativity literature on this, because from my understanding, the origin of that was that they were, trying to get fractal quantum mechanical paths to work in the context of, general covariance and things.
All right. Okay. We better go and try and get Wolfram model multi-way systems practical stuff to work. That's the mission. And then, yeah, I mean, we're getting close to understanding the stuff. I think we need to look at, so tomorrow maybe, if we have a chance, we can look at some actual geodesics in actual meshed spaces, so to speak, which I think will give us better intuition about these things. All right. Sounds good.
Okay, right. Talk to you soon.
Okay, see ya.
Bye.
Bye.